Hello guys, welcome back to the YouTube channel of the Concept Guy, and in this video we will do this problem in ASPEN Plus. Okay, so let's see how we proceed and how we get the results for the same. We open ASPEN Plus and select new and a blank simulation, and let's create it. So according to our questions, we are doing a combustion of methane. Okay, so let's select the components in the properties tab. The components are methane. Then in the air we are actually having oxygen and nitrogen. Okay, so oxygen and nitrogen are there in the air. Then we have carbon dioxide and water as the products of the combustion of methane and oxygen. So carbon dioxide, CO2, and water. Okay, yes. And then we have hexane and heptane that would be input to the heat exchanger later on. So let's write hexane and heptane. Let's click on next, this N button here, and let's select a method. So a property package, say HYSYS, and let's go to the simulation window. Here what we first need to do is mix the air and methane gases. So this is a methane and let this be air. So let's write air, and this will be methane. So when they are mixed, and we need to send them to a reactor for combustion. So for here we have so many reactors, but we must select one that is convenient to this question, that is RStoic. That's the stoichiometric reactor, because we know the stoichiometry and the completion, that's 100% completion. So let's join these. Okay, and then after the reactor we need a heat exchanger where we have 4 streams, not just 2 streams. So we will use this heat X because we have 4 streams here. Okay, and let's rotate it because, okay, let's see that. Let's first attach the streams. So the exhaust gas will go to the hot, because after the reaction heat will be released and this stream will be hot, and we need to cool it down to, let's rotate it first. Let's rotate it, and yes, that's fine. And we will cool it down. So, and there will be a cool stream. Okay, the hot stream comes up here and goes through this and cools down to the exhaust gas, and this is the hexane heptane stream. Okay, yes, this is the hexane heptane stream. Let me just delete this one. Okay, let's press delete. Okay, yes, and this is the hexane and heptane stream. Okay, so everything is ready. Let's just rename these. This is my exhaust. And this is my hexane and heptane. So this is my cold stream actually, which will cool the exhaust gases, and this is my hexane and heptane stream. Everything seems to be ready, and we can just put in the data. So this is the overall flow sheet. Okay, it's the exhaust gases are hot and they need to be cooled down with hexane heptane. So let's put in the temperature, pressure, and the mole flow rate. And this is the methane, so mole fraction would be 1 because there is only methane in this. Now let's put the input of air. Air is also at the same temperature and pressure, and the mole flow rate is 1000 kilomole per hour. Next we have in the air the mole fraction of oxygen is 0.21 and nitrogen is 0.79, hence the total mole fraction is 1. Okay, and this goes to the reactor. RStoic means stoichiometric, and let's say you did this, like you mentioned the pressure and temperature, but in the question it is given as adiabatic combustion chamber. So the duty, okay, so we need to specify the duty as 0. Okay, why as 0? Because there is no heat transfer from the reactor to the surroundings or vice versa. So the duty, that's the energy or the heat, is 0. That's adiabatic. That's the definition of adiabatic. And hence the reaction, we need to create a new reaction where methane and oxygen will perform in the combustion and give CO2 and water. So let's see the stoichiometry, and it's 1 2. Okay, minus sign because of that is in the reactant, and this is the product, so 1 and 2. So make sure you enter this correctly, and the fractional conversion is 1. That means 100% conversion. Okay, so that's the benefit of using RStoic, because we actually know this data as per the question, and we know the stoichiometry as per as the percentage conversion of methane. Next, we need to specify the input to the heat exchanger. So let's use shortcut because that's a normal general method, and let's put the hot stream outlet temperature that is given to us as 250 degrees Celsius. So this is the exhaust, which will be cooled down to 250 degrees Celsius. Hence everything is complete, and this is what we are left with. We are left with the heptane and hexane stream, and as per the question, 25 degrees Celsius and 1 bar, and the total flow rate would be is 100 kilomole per hour. So mole fraction of hexane and heptane here are is given as equimolar, so that means 0 0.5 and 0 0.5, because they are equal and their sum is equal to 1. Hence we are complete, and yes, you can run the simulation with this button. Press this button and the simulation will run, and let's see what are the results that we get. Or you can click on this next to see what all inputs do we need. Results available here, and there's a blue tick, that means everything's okay, everything's complete. Okay, and let's see the result for this. Go to stream summary, and here let's scroll down towards the left, and let's go to the streams section in results summary, rest streams, and here we have all the data of the streams. So we need this hexane heptane, that's the temperature of this stream, hexane heptane. Please do subscribe, and the temperature here is in degrees Celsius 441.54. That's the hexane heptane stream that was used to cool. And let's see the mole fraction. This we have hexane and heptane. Yes, that's the particular stream whose temperature we need, and it comes out to be 441.54. That's the temperature. So if you really like it, please do try it yourself, and please like, share and subscribe, and don't forget to actually find this report also, because sometimes it's helpful to know more about the whole process. Thank you.